Aloha and welcome. In this video, we're going to be talking about symmetric encryption, the BlockCipher. So let's go ahead and open up our text here. So we've got symmetric encryption. We've talked about the stream cipher before. Now we're going to be talking about BlockCipher. So BlockCipher is going to be a symmetric cipher that encrypts a data block. And that data block, it's going to have a certain size. So it's going to, let's say you've got a 64-bit block like IDEA, like they're talking about in the example here. You're going to take your message, your plain text message, and if you've got 64-bit blocks, you're going to divide your message up into 64-bit blocks. But unless you've made your plain text exactly, a multiple of 64, you're going to come up with a last block there that's only partially filled. So then we're going to have to do what we call padding. So padding is the process of adding bits to a plain text last block. And that just kind of, it finishes padding it out to be a full block there. So the example they give here, if you've got a block size of 64, you've got an 84-bit plain text, then you're going to have 84 minus 64 left over bits. So that's going to, give you so many, and then you've got to get the rest of those up to the 64. So that's how you're going to go ahead and create these. You're just going to have to pad out the last number of bits in it. So they give you an example here in participation activity. So you start. It's going to go through, you've got the first block here, then you've got the second block, and then you've got the third block. And it's going to fill in the last, oh, hold on, let's wait a second. So it's smaller, so it's going to take all these, you see the 0, 1s back here in green, it pads it out to finish it off. So all the cipher text blocks have the same size as the BlockCipher's block size. So that's why we need this padding. So the next part we're going to have, a quick note about these. So BlockCipher is more efficient than a stream cipher when the size of the plain text is known before the encryption process begins. Otherwise, if you don't know what it's going to be, the stream cipher is going to be the most efficient. And then we've got some questions, some exercises. Then we talk about modes of operation. Modes of operation are talking about how are we going about actually creating these ciphertexts. So there's a number of different modes of operation here. There's 5 specific ones. One is ECB, the electronic code book. This is an older one. This is not a good idea. Unfortunately, if you encrypt the same text, it'll give you the same ciphertext. So if you redo it again, it'll give you the same thing. And using that information, you can crack this. So you don't want to be using ECB out there. There's something called Cipher Block Chaining, which is a little bit better than that. And Cipher Block Chaining is going to use something called an initialization vector. So what you're going to do is you're going to XOR you're going to essentially at each step you're going to take your plain text, you're going to XOR it with the previous ciphertext. But on the first time through, you don't have previous ciphertext, so you use this thing we call an initialization vector, and that's just a random bunch of 0s and 1s. That's the block size. You're going to use that. You're going to XOR it with then you're going to encrypt it. And these are pretty complex, so I've made notes. I actually went and made graphics for most of these. So if we go into our study notes, you'll see that I've noted the most important aspects of each one of these. And I've written up a diagram of it. I couldn't find any good diagrams out there of it, so I went ahead and made it myself, so don't laugh at these. But this shows you, like, this is electronic code book. What it's going to do is it starts with plain text. It breaks it up into the different parts. It pads it as necessary. Then it goes ahead and encrypts it. And after encrypting it, you get your ciphertext. And then at the end of it, you just concatenate these back into your big ciphertext. The problem with this is if you've got one that's the same, it'll look the same when it comes out the other end, and that's not a good thing. So the next part is cipher block chaining. The notes I have here on it, each plain text block is XORed with the previous ciphertext blocks. We talked about that. You then encrypt that, and the ciphertext blocks are computationally chained together. So what that means is, like we said, if you're XORing it, the current plain text with the previous ciphertext, that means that your ciphertext that you're going to come out with is connected mathematically to that previous ciphertext. So why does that matter? Well, let's say that your ciphertext at some point in the process gets corrupted. that means that you're going to have corruption that goes through in all subsequent blocks. So that's one of the problems with cipher block chaining. So, and also keep in mind, like I said a minute ago, in the first round, when we're taking the plain text, we have to XOR it with something. So we create that initialization vector. We just come up with a random bunch of zeros and ones to XOR it with. Then we encrypt that. Then after we've encrypted it, we've got our ciphertext block, and then we use that to XOR it with the next plain text. And that looks like this monstrosity right here. So here's your cipher block chaining. So you've got your plain text, you've got your initialization vector that goes in there in your plain text. You XOR that together, you apply the secret sauce, the encryption, then it comes out as a ciphertext block. Then you use this, and you use this to XOR it with the next plain text block, encrypt it, you get your next ciphertext. Then you take that and it goes into the XOR with the next thing of plain text block. So you see that if you were to have something happen with ciphertext 1 here or ciphertext 2, all subsequent blocks are also going to be corrupted. So that's one of the problems. We say that the error propagates throughout the rest of them. So that's something that's an issue. Then we have we have cipher feedback and we have output feedback, and that's going to do something similar to before, but what it's going to do is it's going to take a part of the ciphertext and use that in the XOR process after it. So cipher feedback, that operates as a stream cipher. So an IV is used to in the encryption process of the first plain text block, just like before. And then ciphertext blocks are computationally chained. So once again, we're going to have those dependencies. So if we have something go wrong, those errors are going to propagate there. So each plaintext block is encrypted, and then it's XORed with the previous ciphertext block to produce the current ciphertext block. Then encryption and decryption processes are the same, and the errors are going to be propagating. The output feedback, OFB, is a little bit different because in this one, the errors do not propagate. So this one generates the key stream blocks, which are XORed with the plaintext blocks to create the ciphertext blocks. Then the chaining dependencies do not, so it doesn't have chaining dependencies in this mode. So each block is going to be created independently of plain text and ciphertext block. This is something to remember. You'll see questions about this. So this is the only one that has, the only one where the block is created independently of plain text and ciphertext blocks. Then encryption and decryption processes are the same, and errors do not propagate. The last one we're going to look at is counter, and counter essentially is one where you create something called a nonce. A nonce is a shortened phrase. It means number used once. So they call it a nonce, and it's essentially a number that they create, any random number, and then they add one to it. So you have a counter aspect of it. So what is going to happen here, this is a little bit different. So we take our plain text and we break it up into our different plain text blocks. And then what we're going to do, we're going to take, and this is really the cool thing about it, you're going to take that number, that randomly generated number, you're going to add a counter to it, and you and the receiver of this message are going to know what the counter is. So you're going to know that every time you exchange a ciphertext block that you're going to increment that counter. So you've got your nonce, which is that number, you add one to it, and then instead of encrypting the message, what we're doing is we're encrypting that nonce plus one. So once we encrypt it, we get this stream of bits. So that stream of bits comes out, and you XOR it with the stream of bits from your plain text from that block 1. Then you take the output of that, and that creates your ciphertext block 1. And then next you go over and you have your nonce plus 2. You encrypt that. Then that creates that stream, and you take that and you XOR it with plain text block 2, and that creates ciphertext block 2. So this, you'll notice that if I have an error here in ciphertext 1, it does not affect the ciphertext 2 or 3. They're independent in that sense. So errors do not propagate. So, anyways, that's the major points of the modes of operation. That's a really tricky section. Took a long time to actually create some of these graphics, so I do apologize for getting the video up a little bit late. But go ahead and look at these. Next, we talk about data encryption standards, and this is the place where I really feel old, because when I was in graduate school at UH back in 1994-5, One of my assignments in computer security was to write a program to do DES encryption. DES encryption back then was the end all be all. It was like the best thing they could ever think of. So this was really big. Unfortunately, we know that it's extremely weak given the computational power that we have now. So DES is not used. We have something called triple DES or three DES that's used in its place. So let's talk about DES, the Data Encryption Standard here. So it's a symmetric block cipher which encrypts data in 64-bit blocks. So the blocks you're going to be using 64 bits. So the keys that it's using on this, the encryption keys are 56-bit keys. So DES is considered, it's not considered a secure encryption algorithm because a 56-bit key can be broken with modern cryptanalytic techniques. Back in the day, it wasn't so, but now it's considered quite weak. So now we've got the triple data encryption standard, the TDES or the 3DES. It's a symmetric block cipher which applies the DES 3 consecutive times. So you're doing it in rounds. You're doing 3 different rounds on it to create each 64-bit block. So 1, 2, or 3 identical or different keys can be used at each of the 3 DES rounds. So what they're doing is they're increasing that key size by using 3 keys essentially. So the 3 keying options you have there. Option number 1, which is the most secure, you're going to have 3 56-bit keys used in each of the DES rounds. So that's going to be 3 rounds times 50, or 3 keys times 56. That's 168 independent key bits because each one of those keys is different. So that is the most secure option. Number 2, you're going to have 2 independent 56-bit keys are used in the DES round for a total of 2 times 56 or 112 independent key bits. So that's a little bit weaker. Then option 3 that you have is the least secure, but it gives you backwards compatibility because you're going to be using 3 identical 56-bit keys. So whereas DES was using 1, you're using that 1 just 3 times. So that's going to give you it's the most insecure of the 3, but it's considered much better than just regular DES. So Triple DES was designed to improve the DES by increasing the encryption key size without the need to design a new symmetric block cipher. So that's DES. It's still used out there. It is computationally expensive, so it needs hardware to support it. We can say something similar about AES, the Advanced Encryption Standard. So Advanced Encryption Standard, it's a symmetric block cipher as well. It's going to encrypt data in 128-bit blocks, so you can see it's already larger than DES in its original form. So it uses either 128, 192, or 256-bit keys. And again, these are computationally expensive. So, when you're talking about trying to do things on small hardware like IoT stuff and everything else, it can be challenging to do, that kind of stuff, on, lightweight hardware platforms. So for example, here, AES is used by VPNs to create encrypted tunnels, by wireless networks to encrypt data in transit, and by data storage devices to encrypt data at rest. Data at rest is just data that's on the hard disk. And it's also used by HTTPS to secure communications on the internet. So there's going to be talk of encryption rounds. Encryption rounds are basically a set of operations that are consecutively applied to a block of plain text bits during that encryption process. So the number of these encryption rounds in AES, it's determined by the encryption key length. So a longer key, it's going to correspond to a higher number of encryption rounds and a larger key space, but it's going to, well, not but it's also going to make it resistant to brute force attacks. So there's a chart here on it. So you've got AES 128, AES 192, and 256. You're going to need to know those 3 different types because I remember seeing questions back in the day on, which one is which. Just know that AES 128, that's 128. The key length is right there in the name. And the number of encryption rounds are listed there too. So 128, of course, is going to have less encryption rounds. It's going to have a key space of 2 to the 128 because you're dealing with 128 bits. So that's going to come out to this very large number. I'll let you compute that on your own. And 182 similarly is going to be 2 to the 192, which is a bigger key space. And the next one, 256, that's going to have 2 to the 256 bits, and that is ginormous. So know a little bit about that. You're not going to, if you're asked to, compute it, I mean, you could just say 2 to the 256. And yeah, let them figure that out. But yeah, that's a very large number. So anyway, we have some tools here to test your knowledge of everything, mix and match, and then the regular, answer the questions. So go ahead and make your way through this, and I will see you in the next video. If you have any questions, as always, feel free to reach out and let me know. Have a great day. Aloha.